The fundamental task of a nerve cell is to receive, integrate, conduct, and transmit signals. Many neurons propagate signals along axons in the form of action potentials. Action potentials are able to travel great distances along an axon without weakening because the signal is continuously re-amplified along the way. The central molecular players in this process are the voltage-gated sodium channels and voltage-gated potassium channels, which undergo cycles of finely choreographed conformational changes. Let's begin with the sodium channels. When an action potential passes, sodium channels open in response to membrane depolarization. Sodium ions rush into the axon, further depolarizing the membrane. Within a fraction of a thousandth of a second, however, the sodium channels switch to a new inactivated state, in which they are closed, but now also refractory to reopening. This inactivated state contributes to the falling phase of the membrane potential. The sodium channels then reconvert to the closed state, ready to be opened again when the next action potential is encountered. Let's examine the changing state of the sodium channel during an action potential. When no stimulus is present, the sodium channels remain closed, and the electrical potential measured across the membrane remains constant. However, if a depolarizing stimulus is applied by a brief pulse of electric current, the membrane will start to depolarize away from the resting potential of about -75 millivolts. Some of the sodium channels will open, permitting sodium ions to enter the axon along their electrochemical gradient. If the depolarization is sufficient, even more sodium channels open, and the membrane potential rapidly approaches the equilibrium potential for sodium, about +60 millivolts. At this point, the sodium channels adopt the inactivated state, where the channel is unable to open again, even though the membrane potential is still depolarized. Now let's look at the changes occurring in voltage-gated potassium channels. Similar to sodium channels, potassium channels open in response to membrane depolarization, but only after a delay relative to the opening of sodium channels. This delayed opening causes potassium ions to move out of the axon, leading to a repolarization of the membrane. Delayed opening of voltage-gated potassium channels, together with the inactivation of voltage-gated sodium channels, accounts for the falling phase of the action potential. The sodium channels will remain in this inactivated state until a few hundreds of microseconds to a few milliseconds after the membrane potential returns to its initial negative value. After the sodium channels have switched from the inactivated state to the closed state, the axon is ready to conduct the next action potential. The action potential is propagated along the length of the axon in only one direction. By examining the membrane potential and the state of the sodium channels and potassium channels along the length of the axon, we can see why this is so. As a depolarizing stimulus, represented in orange, reaches our section of the membrane, sodium channels open first, and current flows into the axon. This in turn depolarizes adjacent sections of the membrane, represented in blue, causing adjacent sodium channels to open, and the action potential is thus propagated along the axon. Sodium channel inactivation and the delayed opening of potassium channels prevents the depolarization from spreading backward along the axon.